Hello everyone, I'm Guangyuan Piao from Maynooth University in Ireland, and in this video I'm going to present the approach used for the shared task on the scope detection of the peer review articles at the SDPRA workshop at PAKDD conference. To start with the task description, the task is about given an abstract of a scholarly article, we want to classify it into one of 7 classes or labels as shown in the table. So initially, the data set provided by the organizers have 3 subsets, including the training, validation, and test sets. The data set contains 16,800 examples for training and 11,200 for validation and 7,000 for final testing. So this can be treated as a multiclass classification problem, as one might expect. Well, for each abstract there is only one ground truth label associated with the abstract. So to better tune the hyperparameters of our deep learning models and test it in a completely blinded set, we further divided the validation set into 2 equal-sized subsets for internal validation and internal testing. The evaluation matrix used in this shared task is the weighted average F1 score. And when participating in the shared task, my own purpose is to understand how good the transfer learning performance is based on pre-trained transformer networks designed for sentence or text embeddings, and whether entity embeddings for those mentioned entities in a text help to improve the classification performance. So the figure in this slide shows an overview of the approach with extracted entity embeddings as an optional component. The left part should be pretty familiar for the majority of us, as it just converts the text or given abstract into the text embedding with a pre-trained sentence encoder. The right side is about extracting the entities from the text or abstract using the TagMe entity linking tool, then the pre-trained entity embeddings from Wikipedia to VEG, which are also pre-trained and publicly available entity embeddings, are averaged with the mean pooling strategy, and then are concatenated with the text embeddings from the left side. And finally, the concatenated text embedding is fed into feed-forward neural networks to get the prediction for classification. To give a little bit more detail about the entity extraction step, the first step is extracting Wikipedia entities mentioned in an abstract. So the figure here shows automatically extracted entities for a given abstract using TagMe. For example, the entity graph is extracted from the text graph in the abstract, and the entity edge is extracted from the text edges in the text. And we can also notice that there could be some noisy entities extracted from the TagMe entity linking tool. For example, the television program and the time entities extracted from the abstract shown in this slide are noisy entities, as they are not relevant for our classification task. To the extent, we further used k-nearest neighbors clustering approach to get 2 clusters and simply use the entities within the larger cluster as our set of extracted entities for a given abstract. So the assumption here is the larger cluster should contain the most relevant entities to our problem. So the example shows when the clustering approach is applied, you can see those noisy entities in the orange cluster will be filtered out, and only the entities on the green cluster, such as graph, edge, will be used. The table here shows that BERT model's performance on the internal test set, while the majority of those are used as pre-trained models to extract abstract embeddings, and some are fine-tuned with our dataset. As we can see, the BERT, which is trained on the scientific articles, outperforms other BERT alternative models, which is reasonable given the text for training BERT is trained on papers from the corpus of the Semantic Scholar, which contains around more than 1 million papers with more than 3 billion tokens using the full text of the papers for training, which is more relevant for our task. And also we observe when we use the entity embeddings together with BERT, there is further improvement in terms of the weighted average F1 score. And the bottom part of the table shows the performance of some ensemble approaches using several base models mentioned above, where the numbers in the bracket indicates the index of a base model above. The results show that those ensemble models can further improve the classification performance compared to using base model alone. So we use the ensemble models for the finer submission on the finer test set provided by the organizers. To better understand the classification errors, we also plotted the confusion matrix for the best performing ensemble model for the internal test set to understand which labels make the best performing ensemble model struggle. So each cell in the confusion matrix indicates the number of samples predicted as the corresponding column label, which have the true row label. For example, 570 in the top left cell indicates 570 samples in the internal test set have been classified as LO, where LO is the true label. As we can see that the DC and DS labels are the most confusing ones for the model. For example, the highlighted cells indicate that we misclassified 38 examples with label DC as DS, and misclassified also 30 DS examples as DC. Looking into details of some of the examples might confuse also humans as well. For example, this abstract in the slide is about an article proposing a data structure in the context of distributed computing. Well, DC, which refers to the distributed and the cluster computing, is the ground truth label, but classified as DS, which refers to the data structure and algorithms, which also makes sense to me. Finally, on the finer test set, the best performing one achieves around 92.06% for the weighted average F1 score. As we can see from the details, the approach particularly is not performing well on classifying the CL labels or classes. Thank you for your attention, and I'm happy to take any questions if you have.